Hello everyone, 7:30. Let's get started with our discussion tonight. And today we are starting on a new module on the memory. Memory is very important in the computing system, and we need to know, at least have some fundamental knowledge about the memory systems and how it works, especially with respect to the caching and virtual memory. Uh, for a programmer to have a caching concept and as well as a virtual memory concept is important in the sense like when you grow up in the technological ladder in industry, like you go from junior engineer to senior engineer to principal engineer and so on and so forth, your task could be more concentrated on improving performance of your program, from memory consumption and from runtime consumption. And to do that, memory consumption optimization, you actually need to have pretty much good idea about these methods, uh, or steps that goes into the system to implement cache, what is their impact, how the virtual memory is implemented, what it is impact on the performance, both from runtime and memory consumption perspective of your application. Pretty important concept to understand. So that's why this has been included in the architecture course that for a computer science class. Any question on this topic or anything else? I'm just checking the discussion page as well if there is any. Okay, there is one, seems like. Oh, maybe it's accidentally type in. Yorick, did you like kind of miss
Yes, I
that?
have a question. I don't know what happened. I tried to type it in. I guess it really didn't get noted. I thought it was just hidden.
Okay.
So on page, I think it was 15, the last page in the notes, you said you have these 5 lines of code. Um, it says that the loop part of the code is executed 1,000 times, and for some reason it says the test condition for the loop is executed 1001 times. I'm very confused by this because isn't the test condition executed only after every time that the code inside the loop is executed? So shouldn't it be the same amount?
Mm,
Why does it say one more time?
so isn't that when it's go inside? So this is basically, first of all, let me just point out this is really one cycle or not, and in the large scale, like 1 million cycle or something like that. That one cycle doesn't matter whether we count it or not. But okay, in this code, you may be right. Let's see. So I is incremented each time, right? I is incremented each time. And let's say it is starting from 0, right? So then it goes to 1 and 2 and 3, 4, 5, 6, 7, 8, 9, 10. Yeah, you may be right in that case. Yeah, maybe it has a mistake. So I'm just looking at the note. What did I say? Array ABC, okay, I is accessed 5,000 one time. One, 2, 3, 4, 5, 5,000. So you're talking about the I access of I variable, like
Not the access of I, just the test condition, line 5 versus lines 3 and 4.
okay, 5
Because
execute.
it
Oh,
said lines 3 and 4 executed 1,000 times, and line 5 is executed 1,001 times. And that was very confusing to me because I was like when you go into the loop, then the test condition, if this was like
right,
way
right. You may be right. This may be 1,000. Yeah.
I just wanted to make sure that I wasn't
Yeah,
misunderstanding how this worked.
yeah. So this is like exact counting. And if we are to be very exact with one cycle, as I mentioned, we need to think around that. But on a grand scale of timing computation and the performance computation, that one doesn't really matter. It is
Right.
basically approximated out always. Okay,
Sure.
so but that's a good catch. Thank you very much, Yorick. Yeah, it may be like if it was test condition first and then execution, maybe in that case it would be like that condition. But since the test condition at the end, then probably it is thousand times. Yeah. Okay. All right. Thank you
All
very
right.
much.
Thank you.
Yes, for making this in my attention. Okay. Anything else? Okay. So this is like a very start of the memory hierarchy and the pyramid picture that it's in a slide 4 that is one thing you probably want to understand very well. Uh, so this is the one I'm talking about. So this is like exactly there are like different stages of memory and where the data goes and stored, being temporarily stored, etc. Please have a very clear idea of what is what, right? For example, like this register. Okay, let's start from lower level or maybe middle, like this magnetic disk, solid state disk, those things. Those basically contains your operating system, your application program, everything offline, right? Where you turn off your laptop, everything is stored on the disk. And then you turn on your system, then part of the information stored in this magnetic disk or solid state disk comes over, copied over into the main memory. Not all of them, only the part which is needed and needed at the moment. So there are always these to and fro between the magnetic disk, sorry, it's in general disk system, disk drive, and the main memory that it swaps in, swaps out. That's one process. And another thing is that when you are running one new application, the text code is being loaded into the main memory first from the disk, and when it is done, it is patched out from the main memory, and so on and so forth. So things flow in between these two hierarchy, and not everything is copied back onto the top, but only part which is needed. And same philosophy goes between the main memory and cache memory. Only part of which is relevant are added into the cache, and then only the part which is relevant is added into the registers. Speed wise, register is super fast compared to everything else, and then speed goes down, efficiency goes down as you go down in the pyramid. And the bottom feeder is the magnetic tape, where industry backs up. All the backup goes into the magnetic tapes. Sometimes they're sent into offsite. Uh, Probably you have seen trucks running around what is called is a iron fault or iron stuff, something like that.
You said Iron Mountain in the videos.
Yeah. That one I always confuse with that company name. Yeah, so that one uh, is uh, is one of the backup company, and some of these backup storage companies security is really high. Definitely not less than a military level security, because definitely all the companies secrets goes there, right? If so, they make sure none can crash into their vault, their secret vault somewhere located, who knows. But anyway, that's not the point. From our perspective, that this is completely offline store, and it is nothing live is done on the magnetic tape. All it's done, depending on company's policy, it's back these all the magnetic disk or solid state disk, those disk system are being backed up like maybe daily, maybe weekly, depending on company's policy, are backed up and stored if they are stored offline. And the need for this is that if there is any disaster or someone actually accidentally delete everything from at least their partition on the disk, there is always a snapshot available which you can restore the data from. So this is really and like making the system really secure in the sense that if anything accidental happens like that rm minus rf star, then there is a way to restore the data. So that's the purpose of the magnetic tape. And then this rest of this structure is really like a on the system itself. Like this is offline storage, but it is still attached to the computing system. And then of course this rest of these three are basically when you turn on the computing system, they comes into activation and they comes into this program execution scenario. And one thing to add there is that this is a separate industry. Like usually processor company is not involved in memory business uh, unless it is a really big company. Uh, maybe Intel has some its memory module, especially in the cache area. There are IP vendors which actually provides the hardware component for cache and register files. Main memory, it's a different industry segment, memory industry segment, uh, like SK Hynix, for example, Western Digital, Samsung are the big player there in that market, memory market. Whereas processor is more like this your on a desktop market, it is Intel, AMD processor. On the mobile market, it is ARM processors, Qualcomm, and some parts. Samsung also builds some of them. So processor market and memory market are two different segments. And system companies, like for example, Dell Computer System, they are customer of these two industry, the processor industry and the memory industry. They buy chips from both of them and assemble together on the motherboard to build up your system, like Dell Computing System. Like others are SR Computing. There are Toshiba's laptop and desktop computing. HP even at some point of time has that business. Lenovo is another good company who actually, I think, spinned off from IBM. They generate ThinkPad, those systems. So anyway, the point is that this is a big market, memory market, but it's a different market than the processor industry, and their players, the major companies are list is probably different with some minor overlaps. Uh, okay. Now, now what else? Okay, there are some slides, like especially 5, 6, and 7, they talk about some terminologies, and you need to understand those terms very clearly, especially given some mathematical problem. You need to know what we are talking about. Sometimes it can be confusing. For example, uh, like access time, like or latency. So for random access memory, it is basically time to complete the read and write operation from the time point when the address is presented to the memory. Whereas access time for the non-random access memory like disk drive, it's basically time to place the read-write mechanism at the desired place. So same term, if it is applied to semiconductor memory versus the electromechanical device, it's a different thing. Similarly, with the memory cycle time, sometimes there is a specific category of memory like DRAM. They also involve like a refresh time, which the SRAM, other category of memory, doesn't involve. So on and so forth. So basically, there you'll find there is some confusing term, and some term, same word is applied in two different categories of memory in a different sense. So you need to be very clear of that part. Okay, and then once we understand that, then we moved on to the most important part of this module is the cache memory. And we'll spend a lot of time on this understanding of the cache memory. One of the reason because it actually impacts your application runtime pretty hard. Like if you cannot control cache in a very uh, like time consuming applications, big application, you're running your algorithms on billions of information node, these understanding of this cache memory system will come handy to optimize your runtime. So we'll spend a lot of time on that. And it's a basic, simple philosophy on which the cache system works. It is basically your temporal locality and spatial locality of your software program. It is all observation of your software program, right? So your spatial locality is saying that if you are accessing information from one area of the memory, it is highly likely that you will be accessing its adjacent areas pretty soon in your execution cycle of the program. Where a temporal locality says if you are accessing one part of the memory at one point of time, it is highly likely that you'll be accessing that part or vicinity very soon. Okay, so you can think in a sense like what's your program is. Your program is a bunch of loops, like, and inside that you have little bit of decision making. That's it. Any program you can think of, it is a big loop running around crunching information. Even if you try to think of an operating system, it's just in a loop. It's trying to manage the whole all your resources, right? That's the overall thing. So your software program contains loops, and each loop may contain subloop inside it, and it may have some other subloop inside it. Whether you implement recursive way, iterative way, doesn't matter. It boils down to some loops. And if it is a loop, that means you are pretty much kind of accessing information almost in a sequential basis, right? Sometimes you will find in industry when you write an application that your application is performing badly because you are accessing large number of data sparsely, which is scattered throughout the memory. So one way to improve the performance there is to basically make it contiguous. Instead of storing your information sparsely all around the memory, if you can re-architect your code in such a way that you are actually compacting all the data together in the vicinity, then caching system will actually help you because it will be preloaded into some faster memory chunk, and it is guaranteed over this program if you are actually accessing the memories in a contiguous fashion. For example, like let's say your application is using is allocating a lot of string in a loop, like maybe a billion names in a loop, right? And then also it does some other part processing, etc., which accesses other memories as well. Now, think if you allocate one string object at a time, it may be a situation like this scattered way of organizing your strings. Means like depending on the availability of the memory, your operating system will return you back some chunk of memory, which is here, another next, maybe another 10 over there, another 20 over there, and so on and so forth. That means later, if you want to process all these strings, you will actually start accessing sparsely between different places. But if you know that at least your application program is going to access like at least like 10,000 names, like you know that, then what you can do, you can actually allocate string for 10,000 like string variables together in an array and use that in your program. in that sense, where I'm going from here is that you will find later, if you are into the scientific computation areas, Java is the worst language for doing it. Best is C. Managing C program is hard, but you can really control your memory consumption. For example, this string example, like when you are allocating a string, it's still an object. And when you are writing onto that object, depending on what source string you are copying into that object, at that point, string is going to allocate some memories for you. But if you are going in the C language route, you actually, it's a string is a C pointer. There is no object, nothing. It's just a C pointer, string character pointer. You are allocating memories. And then you can allocate string of such length, you know, like 10,000, 1 million altogether. And then use your own memory management in the program to make your program much more memory efficient. And also, in turns, it will become your runtime efficient as well. But anyway, so you will be hitting those things once you actually go into those higher position in the industry where you need to deal with these things like memory consumption reduction, runtime improvement, all this stuff. There you will need to deal with these hardware features in your programming life. Okay?
Professor.
Yes, you're.
Then if Java is so difficult with it, then why is it seeming to become sort of a standard? Like both community colleges and even SJSU is teaching Java standard.
Okay, that's a good question. Now, look at the Java application space. First of all, its wide adoption is due to this like internet-based application, right? And when it was started, like internet-based application started in the early days, it's a very common problem that you cannot build an application which can run into multiple target platforms. Like one can use your website on a Intel based system, or one can use on the AMD based system, another can use on the Windows. Like, sorry, let me just retract back. Hardware wise, there can be different system, Intel, AMD's, even with the smartphone era, it becomes like Qualcomm Snapdragon, another ARM based processor, everything. There can be on top of that, there can be variation of combination of operating system, which basically add up onto the complexity. Like there can be combination of Windows and Intel, Windows and AMD, Windows and ARM. There can be combination of Linux and all these processor and so on and so forth. So you have very large number of combination of target platform that you want to make sure your web-based application runs okay. With C and C++, that kind of language, it is very hard because compilation target, available libraries and everything is not so standardized. At that point, everyone start thinking about a language for internet. Okay, and then there are several language. For example, there was Tcl, one consideration, and there was I think Ruby and Java and all these candidates, and somehow Java won basically. Especially Sun Microsystem that time promote Java big time. It was a big player. It won the market, and it has these. The concept of this virtual machine or the virtual, what is that called? What is that? You run it always.
Java Virtual Machine.
Yeah, Java Virtual Machine, JVM, right? JVM is the only part which is compiled across different platforms. But each platform, once the JVM is ready, that is a common program, and is installed for all these different platform combination, then your Java program interacts with the JVM. And it's basically make the internet-based programs to be deployed widely very easily. And it also follows all these object-oriented protocols and paradigms, so that software engineering maintenance for large applications is easier. And since internet-based application is widely used in the community, that's why we actually teach Java very well. One reason, it is popular, it is widely used in the internet market, and you have a lot of jobs, right? But you won't heard Java is used in the like supercomputing context. And if you talk to any language person, like who develop languages and deals with language every day, they'll say, okay, Java is one of a worst kind of language. Okay. But it is more like an who came first. For example, Windows, almost everybody had Windows because it's buggy, it has some jitter, this and that. But look at every industry at Windows Enterprise Server, right? So it is not really always one-to-one map what is good and what is in the market popular. Okay. So if you go in an environment where it is actually compute intensive market, computing like a supercomputing, scientific computing, EDA market, electronic design automation, the one I work in, those areas actually deploy object-oriented level C++, like not Java. C++, and even if you look at the program inside it, C++ is kind of an outer shell, inner optimization always done at the C programming level, because we can control things very low level. Okay, so this is kind of an application and perspective point of view that Java is widely adopted. Java is that's why taught, because there are a lot of job market in the application development and others. But language strength wise, Java is not very much suitable for compute intensive jobs. Make sense, Yorick?
Sure. Thank you.
Okay, that's a good question. All right. Now let's see. How is the project going on? I can make a poll. Let's see. Your project status, you can make it anonymously. Let's take a minute to complete that. Your project 3 status, here it go.
Professor,
Yes.
are you taking questions about like the project and Verilog right now?
Oh yeah, sure.
I'm just like working on the unsigned multiplier uh, like propagating circuit that you told us to do, and
Mhm.
I don't know why, but I'm having like the hardest time just changing one single bit of the output, and I was just wondering if maybe we could do a demo of like how to change like a single bit of the net. You know what I'm talking about?
Mm,
Like
can you
with
send me an email? Maybe it's better to communicate over email.
yeah, sure.
Or if it is a generic, can I put it in a discussion? I need to, look at
No,
it.
I think it's pretty generic. It has nothing to do with like how to specifically
do the
Okay.
multiplier, but yeah.
Okay. So can you put your question in a form, like in the discussion, so that I can
Yeah.
look,
Okay,
and
I'll do it.
I'll probably then upload some sample code to do that.
Okay.
Okay.
Okay. Thanks.
Okay, I think we can close the polling and I can share the result with you guys. Okay, 8 of you guys have not started yet, 24%. And your project is due exactly 1 week from now. Okay. And majority of you are started but falling behind the schedule. So again, reminder that is exactly 1 week from now you have the deadline, and that's a hard deadline. We cannot move around. Okay. So make sure you put your steam for these 7 days and get it work. To note, like even if you cannot complete data path and control module all the way, make sure your lower level module actually works. I have points for each of these lower level module that I wanted you to make. I will test them, and based on that, you will get point. I have seen, like, even if someone does not implement even a bit of data path and control logic at all, they can reach like 80% mark point at least. Maybe it's more depending on how much bonus you get and so on and so forth. So it is pretty important that you build and test your low level components like D flip-flop, register, 1-bit register. Those things are pretty important. And test bench wise, you can actually help each other. Like you can distribute code among your study group, and you can share your test bench with each other. Not the implementation, but test bench you can share among yourself. All right. So hopefully that will help you to submit them in time. Next week, we have this deadline. Okay. Let's do a pop quiz. So go to your, let me see. Just hold on. Please don't go right now. I need to set that up. Okay, please go to Canvas, find pop quiz number 8, and then hit yes to this poll to whenever you are ready to enter the password. Hit go. Okay, 21 of 35, 22, 26, 27, 8 more to go, I believe. Of 35, I'll wait maybe 10 more seconds. All right. Here is your password. Okay, so I think time is up for most of you. Let me share the statistics with you, quiz results. Okay, so you see that high score is 100% with average 58%. Average is not that good. We need to follow through. Please make sure you are up to date with your study on this class. Okay, 8:15. Let's take 5-minute break. Let's take 5-minute break, and 8:20 we'll be back. Okay, let's come back from the break. Let's do a problem. Okay, that's a problem regarding this memory access. Okay, okay, here is a problem. Okay, uh, so we are trying to compare boot time, operating system boot time between two systems. One using the traditional disk, the electromagnetic rotating disk. Probably some of you have or have used it already, or maybe have it using it right now, which uses the transfer the data to the main memory at a minimum unit of 2 kilobyte block of data. That means it has to adjust its read and write head per 2 kilobyte of block data at access. And it has an average access time of 1 millisecond. Remember what is the average, what is the access time defined for this kind of memory. Now its transfer rate is about 100 Mbps. Here is, it is a megabits per second. Now another computing system which has a solid state disk, probably some of you are using that already, some of you have seen it in the market. So this system has a transfer rate to the main memory at a minimum unit of 1 kilobyte block of data, and it has access time of 50 microseconds per block of data transfer, and a refresh time is 250 microseconds. So that means each block, after each block is transferred, it needs to spend 250 times to gather itself around, and that's a refresh time, and then can start a new block transfer. Now assume both the system runs a Linux operating system, which initial size of 2 megabyte to be loaded into the main memory during the boot time. Which system will boot faster and how much? So we need to calculate the ratio. So I hope this problem is clear to you. Any question on this problem? Otherwise, we will do this problem in group. Let's take about 15 minutes to discuss these with your peers. Just move around. Okay, I'm opening room for all. Let's spend 15 minutes. Okay, I think our time is up. Let's turn to group 15. Ahmed, Brandon, if you guys have come to a conclusion on this problem, you want to share? Ahmed Razdan, Brandon Wenji, Brandon Ong. No. How about maybe group 14? Jack Cow, Rajan Perry. Do you want to share your thought on this problem? No. Okay, anyone wants to volunteer, solve the problem, or at least can show us the approach or discuss the approach?
I guess if no one's gonna go, I can go. I by no means have the right answer, but this was how I thought about the problem.
That's a confidence that you know it's a wrong answer. Come on.
Yeah, I mean, if no one's gonna go, someone has to go, right? So I guess it'll be me. I'll just go. And I might completely butcher the problem, but this is what I have though.
Okay.
So the
Group
problem.
4 also had problems, so we're all in the same boat.
Yeah, that's right too. So we have 2 kilobytes of block data, and we know that it's the operating system has an initial size of 2 megabytes. So I divided the initial size by the memory that we have to transfer. So 2 megabytes divided by 2 kilobytes, which is 2 to the 20th divided by 2 to the 10th. And that just gives you 2 to the 10th, which is 1,244 bytes. And we know that it's given that each byte, the average access time is 1 millisecond. So if it takes 1 millisecond for each byte, it would take us 1,024 milliseconds to access all of it. And once you access the memory, I was pretty much lost.
Okay. So did you get the chance to work on the solid state disk system?
No, not actually. We just tried figuring out like potential ways to get to the answer for the first one.
Okay. Yeah, I can. If anyone else wants to share their thought, I can pretty much go after that.
Yeah, like I said, we were also lost. We didn't actually come to an answer either.
Right. So
I think we figured out how to work it out, but we didn't actually work out the answer by ourselves yet.
Okay. So why don't I share my solution with you guys and see if you're on the same page on these. So as you are saying that Vajat is saying a total number of blocks to be calculated. So for traditional disk, since the block transfer size is 2 kilobyte, so we divide them. So 1024 blocks, and access time, which is basically a time to place the read-write head onto the right location, right track, right sector on the disk. So that will take, according to our problem statement, is 1 millisecond. So we can multiply 1024 by 1 millisecond. It takes about 1.024 second. Now each block will be transferred to the main memory with 100 Mbps, megabits per second. So that from there we can calculate how long it will take for each block to be transferred. So it is 2 kilobyte by 100 MB second, that means. So we little bit work on the unit, kilobyte to kilobit, which is 16 kilobit by 100 MB. and then it boils down to 0.16 multiplied by 2 to the power minus 10 second. And we have that many blocks to transfer. So multiply by 1024, it comes down to 0.16 seconds. And then total time we add this transfer time, this transfer time and access time of the traditional disk, it comes down to 1.184 seconds. Now for the solid state disk, we have a little bit different parameter. It's transfer 1 kilobyte block, like this. This is the size, and there is an access plus refresh. Let's compute it together to make our life simple. Data transfer is needs 50 microsecond, and then refresh is 250 microsecond. Total it takes 300 microsecond. Of course, one can argue that, hey, the first transfer doesn't need any refresh time. It has to be one less. But with this huge amount of data, whether you count that, not count that, does not really make any difference at the end or outcome of the result. So it's kind of an approximation step to make our life simple in this calculation. So bottom line, each block transfer would be done in 300 microsecond, and this many blocks we need, 2 MB data by 1 kilobyte, little bit work on the unit side, and it basically 2048 number of transfer to be happen, multiplied by this 300 microsecond, it's 0.6144 seconds. So we basically performance of this by performance of this is execution time of this by execution time of this, which brings down to 1.184 by 0.6144. It's almost approximately 1.93, almost like 2 times faster this solid state disk system compared to the traditional disk. In fact, you can probably would have experienced that if you have used both the system. Many older laptop has this traditional rotational disk, electromagnetic disk, and modern laptops has this solid state disk. You'll see a stark difference between boot up time between these two systems. This is one factor. This is not the whole story about booting time, but this is like one factor. Question?
Professor, how realistic are these numbers?
These are
Compared.
kind of made up number, just for the sake of the problem and to understand, to make sure you understand these terms and stuff like that.
Okay.
Not, in other words, not realistic at all. Okay, we are overboard by 2 minutes. So let's stop here tonight and see you all on Thursday.